Geometry, lesson 9.5. We're moving on from prisms and cylinders to volumes of pyramids and cones. Here are some specialized formulas for polyhedrons. Be sure to record these in your notes. These formulas will be repeated later on and introduced in a further slide. So, according to Cavalieri's principle, a pyramid and a cone, if they have the same height, and we'll demonstrate that. I actually have a dotted line. That's the same height for both of these. You'll note that the height intersects the base in the figure to the right. It intersects the base at a 90-degree angle and also to the cylinder on the left. Each plane that is parallel to the bases. So in the cone we're talking about this cross section right here, which is parallel to the base, and this pentagon which is also parallel to its pentagonal base, with equal areas. So if this circular cross-section has an area that is equal to the pentagonal cross-section, then the two figures will have the same volume. The formula for prism's volume is volume equals base times height. And let's take a look at our prism. It has triangular bases, and there are two of them. And the area of the base, which is UVW, is illustrated, and the height h. Now we're not talking about prisms in this chapter, but you're going to find out why I just reviewed prisms right now. If you are to take this prism and divide it using planes, and if you remember back to a previous unit that we just covered, a plane can be create a cross-section inside of one of our figures. It can be parallel to the base, it can be vertical to the base, it can be diagonal to the base, and so forth. If you divide this prism into three separate solids using planes, we have these three solids that add up to the whole prism. So on the left we have XUZ, and then in the middle we have YZU, and that's this basically this light colored prism right here. And then on the right we have ZUW, which is this whole prism in the front. These three together, when added together, their volumes, when added together, will equal the volume of the prism. This is really hard to conceptualize. This is part of Cavalieri's principle. And take my word for it that we could do this. If we took some of the figures that we looked at in class and divided them with planes and filled them with sand, we would be able to divide some of the prisms that we had there into three separate areas, and we would be able to take those planes out and they would fill the whole prism. So pyramids, when we took this prism and divided it, we created pyramids because we took away one of the bases for each one of these. So pyramids A and C both have congruent bases. in pyramid A we have base XYZ, which is congruent to the bottom base, which is UVW. So very quickly you can see that they have equal bases and they have the same height. So consequently, using the volume formula of V equals B times H, we can see that A and B are congruent. Pyramid B actually is also congruent. It's reversed and it's a little difficult to see, but if we compare YUZ here in pyramid B, if you look at pyramid A, you'll see with the dotted lines that it would fit right in there. And if you go to pyramid C, you can see that this darker piece, ZUV, will also fit in that prism. So essentially B, though it's a composite of both A and C, it is also the same volume as A, which means it's also the same volume as C. Because the volumes of A, B, and C are congruent and can be divided by 3 congruent pyramids, the volume of each pyramid is 1/3 of the volume of the prism. So all of this has been to show you that we can derive a formula from the volume of a prism base times height for a pyramid. And here it is. The volume of a pyramid, theorem 9.5.1, is 1/3 the product of its height and the area of its base. So we have the prism, once again, if we were to do a cross section, it would be 1/3 of the base times the height. So let's look at an example. Here is a pyramid. We have a height of 321 feet and a side length of 591 feet. Here's our formula, and 1/3 base height can be derived into a more specific formula. This is a square base, so we can say 1/3 side squared times the height. That'd be 1/3 591 squared times 321, and the total volume would be 37,373,067 feet cubed. Theorem 9.5.2. The volume of a circular cone is 1/3 the product of its height and the area of its base. So what we've done, just like we had done previously between prisms and cylinders, we now can substitute the circular base into our formula for base, and for the big B of the base, and we have 1/3 base times height, or 1/3 pi r squared times the height. Now in your book they had a picture of an ice cream cone. So this is the direction the ice cream cone would have been in. I'm going to turn it around to something a little more familiar, and we now have our cone with our height. It also has a radius and a diameter. I've drawn the diameter in there because they've actually asked us to solve for the diameter in this figure. So volume equals 1/3 pi radius squared times the height. We were told that the volume in this problem is 250 centimeters cubed and that the height is 15 centimeters. So I've added my heights to this drawing and we'll solve. So we have the basic formula for the cone, 1/3 pi r squared h. We know that the volume was 250, so we'll substitute that value. We have 1/3 pi r squared times the height, which is 15. We have 250 equals 5 pi r squared. That was 15 times 1/3 is 5. And now we divide both sides by 5 pi, and r squared equals 50 divided by pi. That means that r equals the square root of 50, which is approximately 8.0 centimeters. Sorry, had to make a little change there. So the square root of 50 divided by pi is approximately 4.0 centimeters. And in this problem, we were solving for diameter. So I will go ahead and the diameter would be twice the radius. So the diameter would be 8 centimeters. Example 3. Find the volume of the oblique pyramid with a regular base. Dimensions are in feet. One of the first things I want to point out, even though this pyramid is oblique, we can still find a height by dropping a line from the vertice perpendicular to the surface of the base. It'll just be outside the base. And the base of this pyramid is a regular heptagon, which is 7 sides. So what we'll do for area of the base, we're going to substitute the 1/2 AP before we actually add our dimensions. So 1/3 base times height becomes 1/3 times 1/2 AP times height. 1/3 times 1/2 is 1/6. The apothem is 8. And there are 7 sides. And each length is 7.7, and we'll multiply by the height of 22. Doing all of that multiplication, we find that the volume is approximately, if we round to the nearest tenth, 1,581.1 feet cubed. Fairly easy formula to do. These are the more specific formulas for volume that were on your vocabulary slide. Each one of these is basically derived from the volume of a cube. Be sure to put these in your notes. And I wanted to note that if a known formula is not available for unusual figures, that we'll be using the volume addition postulate to find the sum or difference of their volumes. Some of these formulas are a little bit complicated. You really need to be good with your square roots to solve them, and take them slowly. And I suggest you do not use your calculators to solve these initially, because if you go ahead and turn these into decimals at the beginning of the problem will not be the right answer. So example 4, let's find the volume of the solid, and the dimensions are in millimeters. And let's break down this picture. So we'll be finding the volume of a cube, which is right here, the volume of a square prism, and that's this one up here. It doesn't quite look square in the drawing because of the perspective, but you can see by the base units that it is a square base. And find the volume of the rectangular prism. We'll find the volume of each one and then use our volume addition postulate to solve. So, number 1, let's find the volume of the cube. So we'll call that volume 1, and this is the cube. Our volume formula is edge cubed. So the length is 8. 8 cubed is 512 millimeters cubed. Second, we'll find the volume of the square prism. So V2 would be this prism on top of the figure, and it has a square base. So for the base, we'll have side squared times the height. The sides are lengths of 2, so 2 squared times the height of 4. and that's 4 times 4, which is 16 millimeters cubed. And the last piece would be volume of the third object, which is a rectangular prism, and that is volume equals length times width for the base times the height. And we do this when we don't have a regular base. Remember that. If we don't have a regular base, that's a square or a regular pentagon or something like that, we use length times width. So the length is 3, the width is 6, and the height is 5. Now, how did I know that height? Well, this height of this square is 8. This piece is 3, so the remaining piece that shows as a dotted line here will be 8 minus 3, which is 5. 10 times 6 times 5 is 300 millimeters cubed, and we'll add those numbers together, and our total volume for this figure will be 828 millimeters cubed. This picture reminds me of cardboard boxes that you used to play in when you're a kid. So now you know how you could figure out the volume of those boxes if you wanted to. Lesson 9.5 homework. We're going to do numbers 1 through 8, 11 through 13, 19, 21, 43 through 49 as review. So numbers 2 through 8, be sure to use the most specific formula, and here's what number 5 would look like. So we have the base of this pyramid is a trapezoid. So, and don't let yourself be deceived that this is oblique. The height measure here is perpendicular to the base. They actually show that with the little square down here. So we do not have to drop a height. So we have a trapezoid for a base though. So let's begin. We have 1/3 base time height, and we'll change the formula for the base to that of a trapezoid. So it'll be 1/3 times 1/2 height times base 1 plus base 2 times the height of our figure. Or this is the height of the pyramid. So now we will go ahead and substitute values, and we have 1/3 times 1/2. The height of the trapezoid is 2.5, and base 1 is 3, base 2 is 4.2, and we'll multiply by the height of 4. 1/3 times 1/2 is 1/6. We have 2.5 or 2.5 times 7.2 times 4. That's 1/6 times 18 times 4. 18 times 1/6 is 3. So 3 times 4 is 12 meters cubed. Homework example 12 is extra credit 8 points. You would need to make a picture of a cone with the opened end on top, so just like looking like an ice cream cone. After solving for the volume, and I would put the information that you're given on your picture, you'll multiply by the ratio they give you of inches, cups to inches. So solve for the volume first, and then multiply that volume by the ratio to get the answer that they're asking for. Homework example 19 and 21. 19 is very similar to example 4. You're going to be using the volume addition postulate. And 21, you'll also use a volume addition postulate to solve and add the volume of the cylinder and the cone together. So if you need any assistance, be sure to contact me. And we'll be finishing off with lesson 9.6 in the next video.